will make a distinction between what is isoinertial and isotonic, but if you're interested in, for example, muscle physiology, you need to go back to, there's a previous lecture which refers to the principles of muscle physiology, and isokinetics are dealt with in a separate session as part of this series. So what are the aims? Well, the aims of the session are initially we're going to evaluate the different types of strength and then understand a little bit about why these are important and why these relate to particular sporting actions. Once we've established that, we're then going to get into the idea of addressing the practicalities of assessing strength. And we're going to do that in the context of validity and reliability, a theme which is fundamental really to the principles of exercise science, but is actually fundamentally essential to all aspects of science. And then the final thing is we're going to evaluate the different protocols available primarily in relation to isometric and isoinertial strength. So with those in mind, let's start out with a definition. And the definition of strength we're going to use goes back to Digby Sale back in 1991. Yes, there have been alternate definitions that have come since then, but I think actually this fundamentally works very well in terms of drawing a distinction between what is strength and what is power. So here he defines strength as, muscle strength is defined as the maximum force in newtons or torque in Newton meters developed during a maximal voluntary contraction under a given set of conditions. Now, a couple of things to bear in mind. They're referring to maximal contraction. It doesn't have to be maximal, actually. So muscle strength, if we're talking about maximal strength, then absolutely it would be under maximal contraction conditions. But strength is also, in essence, sub-maximal. It can be performed below that maximal level. But fundamentally, strength is a function of either force or torque. And they are our only variables of relevance and of interest. And I encourage you to reflect on that as we go through this lecture, because units are key to our understanding, and these are classed as the SI units in the case of force and torque. And if we're assessing strength, then all we are really assessing is either the force produced or the torque that's being produced. And we'll establish the kind of the differences of those as we go further into this lecture. But that's a really important starting point. And one of the things I'd like you to do is just bear those in mind, newtons or Newton meters, as being the only real units that we can use to assess strength. Just reflect on that. So we then get into this important question, which is, well, we know what strength perhaps is now, but why do we need to assess strength? And this, which is taken from a paper in 2002 by Jarek, is actually a really nice explanation. And as they've written here, it's, well, look, tests of muscle strength have been extensively employed in sports, physical education, ergonomic and clinical practice. Their popularity has been predominantly based on their obvious validity for muscle function assessment and relative simplicity, as well as an abundance of the relevant literature. So the justification seems to be quite clear. We clearly think about strength in relation to sport. There are certain sports which are more strength orientated. There are certain sports which clearly have power at their heart. And that's a really important starting point, which is we have to draw that distinction between strength and power, which we will get to. But as a real hint, to develop power you need strength. So you can't develop power really without having the strength sitting below it. So strength becomes really important in sporting situations. Not surprisingly, it's important in physical education and the notion of physical literacy. The idea, if we're building up components of fitness, one of the key components of fitness that every individual would be looking for is strength. We have clinical practice. Well, in clinical practice, why is strength important? Well, it's important when we think about, for example, dealing with elderly and geriatric population groups. Trying to understand strength of, for example, the lower limbs is important. If we're thinking about whether an individual is suitable to leave hospital and go back home, to live at home, are they strong enough to get up the stairs? Will they be strong enough to get out of the chair to go from a sitting to a standing position, for example? The ergonomics is quite interesting because in ergonomics, it's kind of the interaction between the human and a structure and an object or a feature. So in this scenario, it might be, well, actually, it's kind of the strength maybe to move an object that is of interest. So it might be the strength to move a golf club or a kick a ball or whatever. And understanding kind of the interaction in terms of the strength required to move or propel that object. The other part of this, which is important as they've written here, is this notion of validity. This idea that they do what they say on the tin in terms of most of the tests. We'll deal with that as we get through. Is that genuinely the case? But also, as they are writing, it's actually most of the tests that we use, particularly when we're dealing with isometric and isoinertial, they are actually relatively simplistic to administer, which makes them appealing to individuals both within the field of exercise science, but maybe also in the field, for example, of, say, fitness training and strength and conditioning, where access to sophisticated equipment is perhaps not as easy to attain. Now, in this regard, Jarek then goes on to write something really important, which is embedded within this paragraph here, which is, look, the methods as well as the reliability and external validity of strength testing have often been questioned. A number of factors that affect the outcome of the applied strength tests have been studied. Some of these factors are related to the tested participants. So, for example, differences in age, gender, physical activity, or body composition. While others are predominantly related to various methodological aspects, such as the type of contraction, the starting position, the stabilisation, the gravity correction or test sequence. Now, this is really important because what Jarek is suggesting on the previous slide, they're kind of saying, look, actually, this is why we do this. This is the kind of the rationale for doing this strength testing. But when we move into this section here, they want us to be absolutely acutely aware that there are significant concerns regarding the vast majority of tests that are used. They refer to the notion of external validity. So this is important. We have to understand the difference between what is internal and external validity. So internal validity is internal to the environment in which it was collected. So for example, it might be internal to the laboratories in which you have collected your own data, or the gym in which you've collected your data. External validity is, does what you have done in your environment, is it transferable to another environment? Can it be kind of replicated? It's different to reliability, but can it be replicated? And that has been questioned, that they're not necessarily replicable. And it might be, as they say, it might be a lot of factors that affect this in terms of the participant. But if we take the participant out of this, the area that we're going to really end up focusing on within this session is these kind of methodological aspects. So what contraction is being assessed affects the validity, also has a significant implication on the reliability of the test. When they refer to the starting position, they're simply referring to where is the limb at the start or the commencement of the activity. So for example, if you're doing a grip strength test and you've got your arm raised up, and then we drop the arm down to our side as we're doing the measurement, we'll actually produce different results to if we have the arm just held vertically, or even if we have the arm at our side with the elbow at 90 degrees. The starting position affects the outcome, which therefore affects the validity of the data. The stabilisation, well, within stabilisation, it's, if we think about doing, say, 1 rep max testing, let's say you're doing a squat. In a squat, unless we are actually well fait and well rehearsed in doing 1 rep max testing and lifting with free weights, actually our stabilisation is probably quite poor. We have poor control. If we have poor control, the validity of the test is lost because we end up recruiting muscles and having motor coordination from muscles that are not actually primarily involved in the action of interest. There is then the notion of gravity correction. Do we do gravity correction? Remember that in any motion where there is movement, this is where predominantly we're assessing torque. where there is torque being assessed, and again we'll show you why torque is important, gravity must play a part. So if you imagine that you are doing a knee extension, sorry, a knee flexion, apologies, you're going from the point of extension back to the point of flexion. As the limb is moving, gravity is helping in that process from going from extension to flexion. It's pushing on the limb. If we go from flexion to extension, we are working against gravity. So do we and have we in testing corrected for that? And then the final aspect is simply, well, the test sequence. What is the order in which we do this? How many repeats do we need to do? Do we need to have familiarization trials and so on? So all of these become really germane to that kind of notion of validity and reliability in strength testing. So there are a number of key definitions that we perhaps need to be aware of as we move through the remainder of this session and moving forward. We need to be able to differentiate the difference between a contraction that is isotonic and a contraction that is isoinertial. Now this is really important because these get very, very confused. An isotonic contraction, as we've written here, is a muscle action against a constant external load. Typically, an in vivo action cannot be isotonic because a constant resistance or load imposed on a limb requires a changing force as the angle about the axis of rotation changes. And if you think about that, it's a very logical reason for this, which relates to the length tension relationship of a muscle. So if we look at this diagram that we've got here, which again has been referred to in previous lectures, so if you're not sure about length tension relationship, go back to the lecture material which is on muscle physiology and force generation. But what we understand, if we look at the image to the left, where we've got sarcomere length on our x-axis and we've got force as a percentage on our y-axis, what we see that when the sarcomere is at its extremes of length, the amount of force it produces is significantly reduced compared to when it is in kind of that mid-sarcomere length, which is in those midpoints of 2, 3 and 4. And what this tells us is, depending upon the point of the range of motion, we get a difference in the amount of force being produced. And this then relates to the definition and this notion that, as it's written, because a constant resistance load imposed on a limb requires a changing force. So if you think about doing a squat, in a squat movement, the velocity at which you can move that bar changes dependent upon where you are in that movement. So when you're deep in the squat, we've got, as the length tension relationship would show us, we've got a significant overlap between the actin and myosin filaments, which would be as indicated as 0.1 on our screen. So we would kind of be, within this domain here. Whereas if we were at the full point of the squat, we've gone to extension, we may well be at this point here in our kind of relationship. But the notion is that because you've got significant overlap here, the amount of force being produced, if we look at the actin and myosin filaments that you see on image 1 on the right, because you've got the overlap between the actin and myosin filaments, it interacts. They interact with each other and reduce the amount of force. So fundamentally, when we're talking about this idea of being isotonic, most actions are not isotonic. They don't have a constant external load because fundamentally the load changes. However, when we do what is called isoinertial, the only thing that remains constant is gravity. So if you go back to doing a squat, in the squat movement, the ease at which we move that bar changes throughout the range of motion, which is why it's not isotonic. It's clearly easier, as the length tension relationship reports, it's clearly easier at these kind of sarcomere lengths around here, not here and not here. So when we take that into account and we do the squat, the only thing that remains constant is gravity. So the majority actually of muscle actions that we do when we do strength testing, the majority are considered to be isoinertial and not isotonic. The next characterization is isometric. And isometric, again, has been referred to in previous lectures, but just as a general recap. So it's a muscle action. The muscle fiber doesn't change length, so the length remains constant. And then we've got our two muscle actions, again, referred to in a previous lecture on muscle physiology and force generation. But the two muscle contraction types that we have are concentric and eccentric. And so under concentric, we've in essence got the notion of shortening, and under eccentric, you've got the notion of the muscle lengthening. So we've got in essence concentric, which is more associated with accelerational forces, and eccentric, which is more associated with deceleration or braking based forces. With all that in mind, we then need to separate out for ourselves the difference between what is force and torque. And we alluded to this at the start of this presentation. And it's really important just to have that, because you remember the definition from Sale was, well, you can evaluate strength either looking at force in newtons or torque in Newton meters. So it's telling us there's something that's changed, that the unit of measurement has changed, and it's changed because it depends upon what it is you're trying to assess. So when we're thinking about force, it is simply the push or pull, the ability to accelerate, to decelerate, to stop or change direction. Those are based upon forces. Whereas with torque, it's the ability of a force to cause rotation. Depends on the force and the perpendicular distance to the center of rotation. So when we think about the notion of a squatting action, in a squatting action, what we go from that deep squat. So we are fundamentally, if we are assessing the strength of the flexors and extensors of the knee, then what we would be assessing is torque, not force. Really important to understand that, because there is rotation in that action around the knee joint. If, for example, we're measuring something using a handheld grip dynamometer, which we're going to get onto in a moment, because there is no rotation involved, there is simply an accelerational force applied to the dynamometer because you squeeze it, then we are assessing force.